All right, step into the interrogation room, detectives, because today we are tackling a massive mystery in modern technology. Have you ever wondered why standard AI models, like those massive language models we literally use every single day, are notoriously miscalibrated? I mean, they are sometimes just so confidently wrong. Well, in this explainer, we're going to crack the case of AI overconfidence. Let's dive right in. To actually understand the problem with our AI, we first need to solve a human riddle. Picture this. You're a doctor, and you're presented with a dilemma. As a medical professional, you know that about 90% of patients who have the flu will develop a cough. But your patient sitting right there on the exam table, they don't care about that statistic. They already have a cough. What they want is the inverse. They want to know, what are the exact chances that this specific cough means they have the flu?
And honestly, this brilliantly illustrates the absolute core of our mystery. See, we easily grasp forward probability. That's the chance of a known illness causing a symptom. But going backward, working from the observed effect to pinpoint the actual hidden cause, that is called inverse probability. And it's a classic problem that routinely stumps human intuition and, as it turns out, standard deep learning models too.
Okay, Section 1. The detective's logic. So to solve this inverse problem, we have to dig up an ingenious 18th century mathematical tool called Bayes' theorem. You can think of this theorem as the ultimate belief updater, or honestly, what I like to call the detective's logic. It gives us a rigorous, mathematically sound mechanism for updating what we believe the moment new clues arrive. And like any good detective, we have to start with a prior. This is just our baseline belief about the world before we even look at the evidence. Let's jump back to our doctor's dilemma for a second. Is it the middle of July? Because the flu is practically non-existent in July. If so, our prior tells us the baseline probability of anyone walking in with the flu right now is incredibly low, maybe like 1%.
Next up, we interrogate the likelihood. This is essentially a hypothetical question. Assuming our prime suspect actually committed the crime, or in our medical case, if the patient actually did have the flu, how likely is it that it would produce this specific piece of evidence, the cough? Well, we already established this is quite high, right around 90%.
Finally, we have to look at the total evidence. This asks a crucial question. How common is this clue in the grand scheme of things? How common are coughs in general from all the other possible suspects out there? We're talking summer allergies, a random cold, or literally just dry air. If 1,000 different things can cause a cough, then any single cough is pretty weak evidence for the flu specifically.
Moving on to Section 2, the evidence filter.
Now let's actually put these suspects together and see this 18th century math in action. We're going to watch how Bayes' theorem operates as a massive filter for uncertainty. I want you to visualize a giant funnel. At the very top, there's this massive, messy cloud of potential hypotheses floating around. These are all the possible causes for our data. Now, as this cloud gets pushed down into the funnel, it first gets squeezed by the prior. This filters out all those highly unlikely background events, like catching the flu in the dead of summer. Then it shrinks even further as it passes through the likelihood, which filters out hypotheses that just don't match our specific evidence. And notice what happens. That massive, uncertain cloud tightens and condenses into one precise, concentrated drop at the very bottom.
That precise, concentrated drop at the bottom of the funnel, that is called the posterior. It is our rigorously mathematically updated belief based entirely on the new evidence. It's the definitive answer to our original question, the actual probability that our patient has the flu, given that they are coughing.
Which brings us perfectly to Section 3, the base rate fallacy.
The crucial point here is that failing to use this funnel, this filter, leads to massive, massive errors. Let's look at a concrete crime scene in the digital world. Imagine a naive Bayes spam filter hunting for the word free in your email inbox. Let's assume only 1% of all the emails you receive are actually spam, and 99% are normal emails, what we call ham. Now, if an email is spam, there's an 80% chance it contains the word free in all caps. But wait, normal people use that word too, right? About 10% of your totally normal emails also contain the word free.
So, you receive an email with the word free. What are the chances it's actually spam? Your intuition might jump straight to 80%. But if we run it through our Bayesian funnel, the shocking truth is that the email is only 7.47% likely to be spam.
Seriously, why is that number so shockingly low? Well, this is the base rate fallacy in action. Because normal emails make up 99% of your inbox, that tiny 10% of normal folks saying the word free creates a massive haystack. It completely overwhelms the actual spam. Without multiplying by that tiny 1% prior to filter out all that noise, your spam filter would just jump to conclusions and give you massive false positive rates.
Section 4. Fixing AI overconfidence.
So, how does this old 18th century logic expose a critical flaw in today's multi-billion parameter neural networks? Why do our most advanced AI systems suffer from this exact same base rate fallacy? Well, the big reveal in our investigation is that standard deep learning models are essentially jumping to conclusions. They're trained by solely optimizing the likelihood, basically just making the training data look probable. They look at it and go, hey, I saw this feature, so I guess it's this category. Bayesian models, on the other hand, rigorously calculate the posterior. They say, given what I already knew about the world and the specific evidence I just saw, here is my calibrated confidence.
And this lack of Bayesian filtering is the primary culprit behind several modern AI mysteries. We're talking about everything from the intractable architectures of certain generative models to the confident hallucinations of large language models to how autonomous agents learn in reinforcement learning. Let's investigate a couple of these suspects, shall we?
Our first suspect is the variational autoencoder, or VAE. It's a hugely popular generative model. The problem here actually lies in the denominator of our Bayes equation, the evidence. For a neural network with 1 billion continuous parameters, calculating the total evidence across every possible parameter setting is a mathematical impossibility. It would literally take forever. So instead of just getting stuck, VAEs use a brilliant mathematical trick called the evidence lower bound, or ELBO. Think of it as a shortcut to approximate the bottom of our funnel without having to measure every single drop.
Our second and probably most famous suspect is the large language model. Have you ever had a chatbot give you a totally fabricated answer but claim it is 99% confident? It happens because standard LLMs output what is called a softmax score. But here's the secret. Softmax outputs are often just uncalibrated likelihoods. They measure how well a token fits the immediate context, but they completely lack a true posterior belief. Essentially, they haven't checked the prior. This is exactly why researchers are desperately working on Bayesian calibration to help these models detect when they are literally just guessing.
Listen, if you take away just one single thing from this explainer, lock this permanent memory aid into your case file. The posterior is proportional to the likelihood times the prior. This incredibly simple relationship is the cure to overconfidence. It forces mathematical models to weigh the flashy new evidence against the grounded, kind of boring base rates of reality.
And that brings us to the end of our investigation. The real world is full of uncertainty, and artificial intelligence is navigating that exact same world right alongside us. So, as you evaluate AI tools in your daily life or at work, always question that confidence score. Is the machine performing a true Bayesian deduction, shrinking that massive cloud of uncertainty down to a precise drop? Or is it just jumping to conclusions, blinded by the likelihood and completely ignoring the prior? Keep asking the right questions, detectives.